Supports develop reactions in response to the weight of the body and loads applied to the body. The body is considered in equilibrium under the actions of the loads and reactions. There are several types of supports for bodies loaded by forces acting in a plane. These supports are usually classified by the kind of resistance they offer to the forces. The first type is the one reactive force. These supports can prevent motion along a specific line of action. A smooth surface and cable provide resistance in one direction only. In another type, the roller and weightless link can also support motion along a specific line of action, but they provide resistance in either direction along the same line of action. We also have the two reactive forces. These supports prevent motion in a plane, motion in two perpendicular directions. The smooth pin and hinge provide resistance in any direction in a plane. The rough surface provides resistance normal and tangent to the surface. We also have the three reactive forces, and these supports prevent motion in two directions as well as rotational motion called fixed, built-in, or clamped. Actual support is produced by building the body into a wall, casting the body as part of a larger body, or welding or mechanically attaching the body to a larger body. The construction of a free body diagram is an essential part of solving any problem. Consider various physical problems as described by space diagrams. In each of the following problems, one or more of the supports shown will be used. A free body will be isolated, and all loads and reactions acting on the body will be shown. In example 5.1, loads P1 and P2 are applied to a bent that may be supported in 4 different ways, as shown in figures A through D. We want to draw the free body diagram and determine the total number of unknown forces and moments. We will neglect the weight of the bent. If we look at figure A, we have a smooth surface and a hinge on the top. So that means we will have one vertical reaction on A and 2 reactions on B. When we look at the figure in B, it's actually clamped to a wall, so that is the typical 3 reaction. We will have a reaction to CX, CY, and MC. In figure C, we have a roller at D and we still have a hinge on E. We will have 3 reactions here. In figure D, we will have a cable reaction. The cable reaction always has the tension reaction, so it's one direction only. We have a roller on G and a link at H. In another example, we want to draw the free body diagram for the uniform beam shown in figure A. The total weight of the beam is 100 pounds. The first step is to draw the free body diagram. In the diagram, you're going to show that the 100-pound force equals the weight of the beam. The beam is uniform. Therefore, the geometric center and center of gravity, G, are at the same point. The 100-pound weight is, in effect, a distributed load and is indicated by a superimposed script capital E. The 1,000-pound force in the example represents the tension in the cable supporting the 1,000-pound weight. TBC represents the tension in the cable BC, and the 2 unknown forces, AX and AY, represent the horizontal and vertical components of the pin reaction at A. That means we have 3 unknown reactions, TBC, AX, and AY. In another example, the beam shown in figure A carries a distributed load. Neglecting the weight of the beam, draw the free body diagram for the beam. Both rectangular and triangular loads were replaced by their resultants at distances 4 feet and 12 feet from A respectively. The first part of the load is rectangular at 2,400 pounds using the equation 300 pounds per feet times 8 feet equals 2,400 pounds. The second part is a triangular load, calculated at 1,800 pounds, using the equation 1/2 times 300 pounds per feet times 12 feet equals 1,800 pounds. There are 3 unknown reactions, Fc, Ax, and Ay, as shown in Figure C. It should be noted that a distributed load can be replaced by its resultant to find the reactions. However, the distributed load still acts over the length of the beam as given.